Hi, I'm Alex from EDD Academy, and this is my video on part 2 of basic differentiation rules. So last time we introduced the derivative of constants rule and the power rule, and today we'll be looking at the derivative of constant multiples as well as the sum and difference rules. So just as review, we'll reiterate both rules we learned last time. So the constant rule said that the derivative ddx of any constant c equals 0. We prove this by looking at the graphical definition of the derivative, which is the slope of the tangent line to the function we're looking at. And let's say this is the graph of our constant. We notice that at any point, the tangent line is a horizontal line, and a horizontal line has slope 0, thus our derivative. We also looked at the power rule, which said that the derivative of any function x to the n, any function to a power of n, is n times x to the n minus 1 power. The original exponent becomes the coefficient of the derivative. And now we'll look at rule 3, which is our first new rule today, and it's the derivative of a constant multiple function. The rule says that the derivative of any function with a constant in front equals the constant times the derivative of the original function. Basically, it's saying that the constant would have no effect on the derivative, so we can just pull it out here. Because this is a pretty straightforward rule, we can jump right into an example. So, example 1 asks us to find the derivative of f of x equals 5x cubed. Now, last time, we just took the derivative of a function like x cubed without the extra 5 in front. But we learned that the constant multiple rule is rather simple, so we can just go about it like this. So f prime, also known as the derivative of x, is ddx of 5x cubed. That's just rewriting our derivative. And what we said we'd do, I'll write the rule on the side here. Okay, so as you can see here, in this case, 5 is our c value and x cubed is our f of x. So we can rewrite this as 5 times d dx of x cubed. Once again, noting that the 5, the constant, wouldn't have any impact on the derivative. And then we can just leave the 5 hanging out in front here and compute our derivative. We learned last time with the power rule that this is 3x squared, where the 3 is our n, and our exponent is n minus 1, which is 2. And simplifying this, that's just 15x squared. It's quite simple. On to the next example. Looking at it now, we can see that it relates some of the stuff we learned in last video, as well as our new rule. So let's get right into it. But before, like last example, I will write the constant multiple rule on the side here. Okay, so rewriting our derivative statement. We talked about how in last video, if we have an ugly square root function on the denominator, we can always utilize negative and fractional exponents to make it look cleaner. So we can take the derivative of 3x to the negative 1/2 instead. And in this case, 3 is our c value, and we can take it out of the derivative, take it to the outside, and multiply by the derivative of x to the negative 1/2. Now we can compute the derivative, leaving the 3 on the outside. So the derivative of this function is, so we take n using the power rule. The negative 1/2 is now the coefficient of our x, so we have 3 times negative 1/2 x, and the exponent is the original exponent minus 1. So negative 1/2 minus 1 is negative 3/2. Simplifying this, we find that our derivative is negative 3 over 2x to the 3/2 power. Now, rules 4 and 5, the final rules we will learn today are very closely related and can be used interchangeably. The sum and difference rules say that the derivative of two functions, f of x and g of x, either added or subtracted, can be computed by splitting up the derivative into taking the derivative of the first function f of x and either adding it or subtracting it to the derivative of the second function g of x. Note I am combining the sum and difference rules here because subtraction is just adding a negative value to something, so they're very closely related. And a lot of calculus, most of math, relates back to what you've learned previously. There's always reiteration in math. And we saw this exact same rule while learning limits. If we have a question that asks us to take the limit as x approaches 1 of x squared plus 3x, we can split this limit up into the limit as x goes to 1 of x squared plus the limit as x goes to 1 of 3x. We split up the limit, compute each individually, and then add them at the end. The same applies for derivatives. So here is a more complicated example than our limits one, but the same rules apply. So we want to find the derivative f prime of x, and that equals the derivative of this whole function f of x here. So the derivative of 4x to the 5th plus 3x to the 4th minus 8x squared plus x plus 3. Using our sum and difference rules, we can rewrite this as, also note that we will be using our constant multiple rules in this question as well, because we have a coefficient different from 1 on almost every one of these terms. So we can rewrite this as 4 times the derivative of x to the 5th plus 3 times the derivative of x to the 4th minus 8 times the derivative of x squared. And then because the coefficient of the x term is just 1, we don't need the constant multiple rule, so we can just rewrite this as plus the derivative of x plus the derivative of our last constant term, 3. So we can compute these derivatives now. So this simplifies to 4 times the derivative of x to the 5th using our power rule is 5x to the 4th plus 3. The derivative of x to the 4th is 4x cubed minus 8 times, and the derivative of x squared is 2x plus the derivative of x is just 1, and the derivative of 3, the derivative of a constant, as we learned in the previous video, is just 0. Multiplying these out and combining like terms, we have this term as 20x to the 4th plus this term is 12x cubed. This term here is minus 16x. And then we finally have the plus 1 at the end. This is our derivative. Note that we can also solve this example much faster, much more efficiently, and the more practice you have with derivatives, the easier taking the derivative of a function like this will look. So once again, we can write our derivative statement. I wanted to make sure to include both the formal method of solving and the faster way because eventually you will use both. So it just saves a lot of writing if we don't take the 4 out of the derivative and multiply by x to the 5th and then add the 3, the coefficient, times the derivative of x to the 4th. You can also just multiply this exponent by the coefficient for each one of these terms. So that looks like 20 x to the 4th plus 12x cubed minus 16x plus 1. And note, we have the exact same answers here, but with much less writing. Here is our final example. We're asked to find the derivative of f of t equals t squared over 5 plus 5 over t cubed. Rewriting our derivative statement, this time in terms of the function t, is d dt of this function. So once again, rewriting it using the constant multiple rule, it's a little bit harder to see, but the c value in this expression is 1/5, so we can write this as 1/5 times the derivative d dt of t squared. And then once again, using our sum rule, because there is a plus sign right there, the c value, the coefficient in this function, in this expression, is clearly 5. So we can write plus 5 times the derivative d dt of t cubed. T to negative 3 power because it's on the denominator. Now we can compute these derivatives while leaving our coefficients out in the front. So this is 1/5 times the derivative of t squared is 2t plus 5 times, and the derivative of t to the negative 3 power is negative 3t to the negative 4. Simplifying this ever so slightly, we can write this as 2t over 5 minus 15 over t to the 4th power. That is our derivative. That's all for this video. Thank you for watching.